For chapter 4, we're going to start talking about scatter diagrams and correlation, and also how to come up with our equation for our line of best fit or least square regression line. There's only 2 sections, so that's what we're going to cover in this one and the next. So to start, we're just talking about scatter diagrams and finding the correlation between 2 variables. So first here we're going to draw and interpret scatter diagrams or scatter plots. The response variable, which is your dependent variable, is the variable whose value can be explained by the value of the explanatory variable, which is also your independent. So if you remember back to algebra, your explanatory or independent would be your x variable, your dependent or your response would be your y variable. So you typically only have your first quadrant because that's your most realistic data, is positive values only. And then we have each data point that represents whatever is being studied, and you might have some dots throughout. So that is what a scatter diagram or a scatter plot looks like. And then we will determine, is there a line of best fit for that scatter plot? Is there a linear correlation in that scatter plot? And work with that. So we're really just focused on linear correlation. It doesn't mean there's not other types like quadratic or maybe cubic or really any type of function, but we are focused on linear in this class. No, it's not always clear which variable should be considered the response variable and which one's the explanatory. It often depends on what the researcher is trying to study. So one thing I thought of is maybe like if we're comparing ACT and SAT scores, we might see, does your ACT score have an effect on your SAT score? So that would make your ACT the X variable and the SAT the Y variable. We could also look at that the other way. Does your SAT score have any effect on your ACT score? So that would make SAT the X variable and ACT the Y variable. So it just depends on what is being researched, okay, or what questions being asked. So definition, your scatter diagram there, each individual in the data set is represented by a point. The explanatory variable is plotted on the horizontal axis, and the response variable is plotted on the vertical axis. So just like I showed you there. So in this first example, the following data is based on a study for drilling rock. The researcher wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. So depth at which drilling begins would be your x value or your explanatory variable, and the time in minutes to drill 5 feet would be the response variable or your y variable. Draw a scatter diagram of the data. So we're going to do this in StatCrunch. The data is located on Canvas, or if you search in the data sets on StatCrunch for drilling rock, it pops up. To look at the stat plot, we're going to go to graph and then scatter plot, scatter diagram. I just said stat plot. you hear it called multiple things. So we'll go scatter plot. You do have to select what your x and your y variable is. So our x variable is depth and our y variable is time. And we really don't need to do anything else here. I'm going to compute it, and that's what it looks like. So you can see here, it's kind of nice. If you hover over it, it tells you that's the data point. So when the when the depth was 120, the time was 7.47. And you can do that with all of these data points. Okay, so it's just taking your depth and your time and making it like an ordered pair x, comma, y, and plotting those. So you can notice there's kind of like a positive trend here. As depth increases, so does the time, which makes sense. So that is what we have for what that scatter plot looks like. So next here, let's look at different types of scatter diagrams. They show the type of the relation that exists between the 2 variables. So our goal in this class is to distinguish if there is a linear relation or not. So we'll get to actually finding the line of best fit or the least squares regression line. But if I draw a line in this data, the data points are very, very close to that line. So there is a strong correlation there. And since it's with a line, it would be linear. Same thing here, strong correlation. Now this next one, it would not be linear. Okay, that looks like it would be more of a quadratic. And then D would also be nonlinear. It looks like it's more like a cubic function. And then if we would have a horizontal flat line that best fits the data, that means that the slope is 0. And if the slope is 0, then there is no relation, okay? So that could be an option, or if your scatter plot just has points all over, and it looks like there's no line that would fit that data, that would also be no relation. All right, so we're really just focused on whether it's linear or not. So it's important to look at the scatter plot first because we want to be sure that a linear model is appropriate, because sometimes it's something else, like maybe a quadratic model would be appropriate, and we wouldn't want to use a linear model. All right, so it's important to look at it. Look at a picture first. We also have positive and negative associated variables. So again, if the slope is positive, remember slope is represented with the letter M. If your slope is greater than 0, it would be positively associated. And if your slope is less than 0, that would be negatively associated. Okay, which means as your explanatory variable increases, your response variable decreases. All right, so talking about the correlation coefficient. So this helps us determine, does it have a strong linear relationship or not? And the term for that is the correlation coefficient, and it's represented with a lowercase r. So it describes it step by step, your points here. So first of all, the linear correlation coefficient is always between -1 and +1. So you're not going to have anything outside of those two values. If the correlation is +1, then that means it's a perfect positive linear relationship between the two variables. So that means every single data point lies on that best fit line that we're going to get to, and our correlation would be +1. If the correlation coefficient is -1, then that would mean there's a perfect negative linear relationship between the two variables. So realistically, that's not going to happen in a data set. You're going to have a whole bunch of data points, and realistically, everyone's not going to fall on a perfect line. So we need to know that the closer r is to +1, the stronger the evidence of a positive association between the two variables. The closer r is to -1, the stronger the evidence of a negative association between the two variables. So a negative correlation coefficient means the slope of our best fit line is going to be negative, and a positive correlation coefficient is going to mean the slope of our best fit line is positive. If r is close to 0, then there is little or no evidence of a linear relation between the two variables. Okay, so note, r being close to 0 doesn't mean there's no relation. It just means that there's just no linear relation. Your correlation coefficient r is unitless, and it's not resistant. So what that means is that outliers is going to affect our correlation coefficient. So your extreme values do affect your r value and your model. So sometimes if there is a distinct outlier, then maybe someone will report the equation and the R value with the outlier and both without the outlier, because maybe that outlier was just an off chance, by chance it happened. Someone happened to be, that number, or there was a data error, it was typed in wrong. So sometimes those are removed to just talk about the main pieces of the data. Again, just caution, if R value is close to 0, doesn't mean that there's no relation, just there's no linear relation. So it could have a quadratic relation or something like that. All right, so here's some pictures. Might be a little hard to see. If you want to see them a little bit better, they are on page 189 in your text. All right, but you can see for this first one, that would be an example of a perfect positive linear relationship because every single data point lies on that best fit straight line. So R would equal 1. This next example, if I draw what I believe would be the line of best fit, not all the data points are on the line, but they're all very, very, very close to that line. So there is a strong positive linear relationship, so our R value would be somewhere maybe around 0.9. And then for example C here, again, the data points are pretty close, but they're not all really, they're a little bit more spread out. So that might be moderate positive linear relationship, and maybe our R value is somewhere around 0.4. We can do the same thing. This would be negative, a perfect negative because all the data points are on the line. So our R value would be -1. This one, our R value would be negative, around -0.9. This one would be -0.4. So notice the difference between a positive and negative R value is whether there is, as your explanatory variable is increasing, is your response variable increasing or decreasing. All right, and graph G there's no linear relationship at all. There's not really a line of best fit I can draw, so R would be close to 0. And then for H, there's not a linear relationship, so R would still be close to 0, but it doesn't mean there's no relationship at all. So it looks like there's a quadratic relationship between those two variables, whatever they are, but we would just state that there's no linear relationship. All right, so these examples, we are going to match the following correlation coefficient values with the appropriate scatter plot. All right, so we got R values of 0.1, 0.8, -0.9, and 0.5. So there's only one negative R value, and the only graph that has a negative correlation would be graph 1. So this would match up with R equals -0.9, and that has a strong relationship, negative linear relationship. And then maybe if I look at, which graph looks like it doesn't have any relationship, that would be graph number 3. So I would say maybe that has an R value of 0.1 because that's the closest to 0. And then between graphs 2 and 4, if I was drawing a line of best fit, okay, the data points would be closer to the line in graph 4 than in graph 2. So we would say graph 4 might have a correlation coefficient of 0.8, and graph 2 would have a correlation coefficient of 0.5. All right. Same thing happens with example 3 here. We just have more to choose from. So looking at all of our different R values, I see an R value of 0. So that means that there's absolutely zero linear relation between the x and the y. So if I'm looking at my graphs here, the one that makes most sense with that would be graph F. So here r would equal 0. There's no linear relation between those points. All right, so I'm going to focus on just the positive r values, so I know my scatter plot is going to rise from left to right mainly here. So the one graph that has most of the data points closer together, with me drawing a line in here, would be graph C. So super close to 1. It's got a strong positive relationship. I go an R value of 0.99. And then between my other two positive relationships, graph A, those are more closer together to the line. Excuse me. Then graph E. So I would say A has a correlation coefficient of 0.90 and E has a correlation coefficient of 0.50. So then if I look at my negative 0.85 versus negative 0.40, remember now it's stronger if it's closer to -1. So the one that would have a stronger negative relationship would be graph D. So that would maybe have an R value of negative 0.85, and graph B would have an R value of negative 0.40. All right. So closer to 1, the stronger positive. Closer to -1, the stronger negative linear relationship. All right, so computing the correlation coefficient and then interpreting whether there's a linear relationship. With that drilling data, let's use StatCrunch to find the linear correlation coefficient. And to do that, I'll go ahead and write down here, we're going to go to Stat, Summary Stats. And at this point, we're used to clicking on columns, but we're going to click on correlation instead. So we're going to go to Stat, Summary Stats, Correlation. It does not matter which one's the X and which one is the Y. You're still going to get the same correlation coefficient between the two, so I'm just going to select both of those. And that's all I'm going to do. And we get a correlation between depth and time. That coefficient is 0.773. R equals 0.773. Now, just thinking about it, it's it's close to 1. It's closer to 1 than it is to 0.5, or closer to 1 than it is to 0. So how do we determine, is that an actual linear relationship? Well, to determine that, we're going to use these critical values. So what we're going to do is determine the absolute value of the correlation coefficient, look at the table that's given there for us, and if the absolute value is greater than the critical value, we say a linear relation exists between the two variables. Otherwise, there's no linear relation. So if we're using that drilling data, we just said that R was equal to 0.773. And the sample, N, is equal to 12. All right, we had 12 different samples. So what we're going to do is we are going to go to the table. And when N is 12, our critical value is 0.576. All right, so the reason we take the absolute value, because remember, we could have a negative linear association. So first, the absolute value of 0.773 is just 0.773. That's greater than 0.576, which is the critical value. Therefore, we can say there is a positive linear relation between, and we gotta be specific here, between the depth at which drilling begins and time to drill 5 feet. Okay, so because our R value was greater than our critical value, then we can say there is a linear relationship. All right. Moving on. Our last objective here is to explain the difference between correlation and causation. So we've touched on this before, but correlation between two variables does not mean causation. All right. So remember, there can be lurking variables behind why something is happening. So I'm going to look down here first because I like this example. For example, ice cream sales and crime rates have a very high correlation. Does this mean that local government should shut down all ice cream shops? No. Okay, the lurking variable is temperature. As air temperature rises, both ice cream sales and crime rates rise. So what it's saying is, like, if we had a scatter plot and this was ice cream sales and this was crime rates, our data points might look like this, okay? But just because ice cream sales go up doesn't cause crime rates to go up. There's just a linear correlation between the two. The reason they're both going up at the same time is by our lurking variable of temperature. Temperature gets warmer, people are more likely to be out. So you might be going out, you know, you're out in the city, in the town. Crime rates may increase, whether it's burglary or whatever, and you also are more likely to get ice cream when it's warmer. So they don't have anything to do with causing one causing the other to happen. We have that lurking variable of temperature. So remember, when data is observational, that would be correlation or association only. Okay, so when you're just observing something, it can only be by, things could only be happening because they're associated. One does not necessarily cause the other. But when you have a designed experiment, that's cause and effect. So you're studying, does what you're controlling have any effect on the outcome? So you could only claim causality when the data is collected through a designed experiment. Okay? And then last, here's just some fun examples of correlation only and not causation. Our X value here, we have chocolate consumption in kilograms per year, and in our Y value, we have Nobel prizes per 10 million population, and it's by country. So you can see there's a positive linear relationship there. As the chocolate consumption increases, so does the Nobel Prize winners. So obviously eating chocolate does not cause that to happen, but there is a correlation between the two. And then our other one here, interesting, our X value is fresh lemons imported to the USA from Mexico. So as those numbers increase, the total US highway fatality rate decreases. So again, that is totally just some kind of correlation between the two. Importing fresh lemons from the USA to the USA from Mexico does not cause U.S. highway fatality rates to decrease. And I do want to note that we have this R squared value up here. We don't work with R squared, we're worried about R. So to find R, we would take the square root of R squared, which is 0.985. But I want to be clear here, we know this is a negative correlation because it has a negative slope, so our R value would be negative. Okay, so there's a very strong negative correlation there with an R value of negative 0.985. All right, so there's a little bit of information about some scatter diagrams and what the correlation coefficient tells us.